Today's topic is BiCMOS logic circuits. So far we have discussed different types of NMOS logic families. For example, NMOS logic with resistive load, depletion load, enhancement load. We have also discussed about different CMOS logic family. We have seen that CMOS logic families provides additional advantages compared to other NMOS logic families. So let us briefly revisit those advantages before we proceed further. As an example, we will consider the case of CMOS inverter. The main advantage of CMOS logic is zero static power dissipation. You know that, right? That is because when PMOS is on, then the NMOS is off, and when the NMOS is on, the PMOS is off. So both PMOS and NMOS are not on simultaneously in static condition. So the static power dissipation is zero because there exists no direct path from VDD to ground in case of CMOS logic gate. Another advantage of CMOS inverter is that it is non-ratioed. That is, the output voltage is independent of the transistor sizing. This indicates that using CMOS logic gate, you can make a particular circuit by using minimum transistor sizes. The third advantage is fast switching of CMOS logic gates. That is because when this PMOS is on, this NMOS will be off. So the total PMOS current will be used for charging this load capacitor. Similarly, when this NMOS is on, then this PMOS will be off. So the total NMOS current will be used to discharge the load capacitor. Unlike other NMOS transistors, there will be no clash between the current of the load and the driver. Please try to recall the discharging situation in case of other NMOS inverters, where instead of this PMOS you have either one resistance or one enhancement load or one depletion load, which are not completely off when V input is equal to 1 or the V input is high. So for other NMOS inverters, when this V input is high, then this NMOS is on. That is true, but the load will not be completely off. So there is also some current that will be flown from this VDD through this load, and that will now try to again charge this CL. So there are two opposite phenomena that is occurring. One is this M1 is trying to discharge this CL, and there is one current from this VDD which is trying to now charge this CL. So these two opposing phenomena will obviously impact the switching speed of other NMOS inverter. However, this will not happen in case of CMOS inverter, because in CMOS inverter, when this V input is high, only this NMOS is on, this PMOS is completely off. So there is only the discharging current, no current from this VDD. So this adds another benefit for CMOS inverter. In spite of all these advantages, it can be seen that the logic families made up with bipolar junction transistor generally shows higher speed than that of logic families made up with MOSFET. For example, as you can see here, emitter coupled logic or ECL, this is the fastest logic which use BJTs instead of MOSFETs. The primary reason behind this high speed is the high driving capability of this BJTs and its high transconductance. High transconductance of this BJTs is quite clear from its exponential relationship of output current with that of its input voltage. However, one of the major issue for these bipolar logic families is their high power dissipation, whereas this CMOS logic family has the lowest power dissipation. So, is there any way to take the advantages of CMOS logic circuit as well as the advantages of bipolar logic circuits, combine them together and get another superior logic family? So, let us see that. Now, consider an situation where a normal CMOS inverter is driving a large capacitive load. So, what can you comment about its delay? The delay will be pretty high, very large delay. We do not want that large delay, we need to reduce it. The question is how to reduce it. What will be the possible solutions? The first solution is pretty easy, right? It is a normal inverter. Increase the width of the MOSFETs, both NMOS and PMOS. When you increase the width of the MOSFET has now the higher current driving capability. So, it will take less time to charge and discharge the output capacitor. Speed will increase, but there is a catch. When you increase the width of this MOSFET, the parasitic capacitance will also increase along with that. Now, the parasitic capacitance will also now act as a load. So, basically this is probably not the best solution for this. What may be the next case? The use of tapered or scaled buffer chain. We have studied this in class, that inverter chain, that use of inverter chain, and finally with the bigger inverter we can connect the bigger load, right? That is a good way to do it, but here is a catch. The catch is it needs large silicon area. So, you have to use so many inverters, okay, one after another, and that will take a lot of silicon area. So, what might be the best other solutions? Okay, in the last slide itself we have discussed that in case of BJT has the high driving capability. So, can we use BJT? Probably yes, but the problem with the BJT is that if we use only BJT or the bipolar logic circuits, then the power dissipation will be significant. To have to reduce the power dissipation as well. So, we have to use BJT along with the CMOS logic. So, basically we have to merge the advantage of the BJT and CMOS, which will form this BiCMOS. Okay, and let us see how this BiCMOS can give the advantages of both BJT bipolar logic circuit and CMOS logic circuit. Okay, in the next slide using and BiCMOS inverter circuit. Let us here consider the example of BiCMOS inverter. For reference, I have also shown the circuit diagram of CMOS inverter. So, let us look into this circuit diagram of BiCMOS inverter. In BiCMOS inverter, first let us consider the CMOS part. Like you can see here, this PMOS and NMOS. So, the same thing, V in is been connected with this PMOS and NMOS. The PMOS source is connected with the VDD, with this VDD, but its drain terminal of this PMOS is not connected with the drain terminal of NMOS. But in case of this BiCMOS inverter, the drain terminal is connected with the base of this NPN bipolar junction transistor, and the emitter terminal of this BJT is connected with the drain terminal of this NMOS, whereas the source terminal is driving another NPN bipolar junction transistor. At output, the load capacitor CL has been connected. Now let us try to investigate the operation of this BiCMOS inverter. Suppose when this V input is equal to low or 0, then let us see what will happen. When this V input is equal to 0, this PMOS is on and this NMOS is off. As this PMOS is on, so one current will flow ID, suppose this current is ID, and that will now act as an base current for this NPN BJT. Now as we have an sufficient current ID, so this BJT will also be on. Okay, this BJT will also be on. So if the base current is ID, what will be its collector current? You know that, right? It will be beta ID. So what will be then the total current at emitter terminal? It will be 1 plus beta into ID. However, in this situation, as this NMOS is off, this NPN BJT will also be off because no current can flow through its base. Okay, so this 1 plus beta into ID current cannot flow to ground like this. So it has to flow to this load capacitor CL. So the CL or the output load capacitor will now be charged by a current which is 1 plus beta times of ID. But if you consider in case of CMOS inverter, when this V in is equal to 0, the CL will be charged by a current which is equal to ID, not 1, but in case of BiCMOS, the current which is charging the CL is 1 plus beta into ID. So we can see in case of BiCMOS inverter, the charging current is pretty high compared to that of this CMOS inverter. So what will happen in case of discharging or the discharge about the discharging current? So for discharging, let us consider the CL is initially charged and we have applied V in equal to 1. Let us see it here. So when this V in is equal to 1 and the capacitor is initially charged, so V in 1, this PMOS has to be in off state. This V in 1, so this NMOS has to be in on. So this is initially charged, so one current will flow. This current will act as a base current. So what will be the collector current for this BJT? That will be again beta into ID. So what will be the total current which will be coming out of this CL? That will be now 1 plus beta into ID. So we can see in case of BiCMOS inverter, both charging current and discharging current is 1 plus beta times of ID, whereas for CMOS inverter, the output load CL will be charged by only a current which is ID. Charging current is also ID, discharging current is also ID. So we can see the much higher current in case of BiCMOS inverter, which means less time required in case of charging and discharging. So less time, if the charging time is or the discharging time is less, that means there will be less delay or it will give the higher speed. Okay. What about the other aspect regarding the power dissipation? Is there any static power dissipation? The answer is no, right? Because when this block is on, this block will be off. When this block is on, this block has to be off. So again, there is no direct path from this VDD to ground at any moment, right? During static situations. So there is no static power dissipation. Obviously in this case we have neglected the leakage current component. You know that, right? There will be always some leakage current both for this MOSFET as well as this BJT. So we are now neglecting those leakage current component, but then we can say there is no static power dissipation in this type of circuit. Here we have briefly compared the performance of BiCMOS and CMOS logic families. This figure shows the variation of delay with increase in load capacitance for both BiCMOS and CMOS logic families. And you can see from this figure that for moderate to high capacitive load, the performance of BiCMOS is far superior than that of its CMOS counterpart. The main reason behind the superior performance is the high charging and discharging current in case of this BiCMOS, as we have discussed in the last slide. And if you think, so what will be the slope of these lines, this line or this line? So if you think it a bit carefully, you will find that the slope of this line is inversely proportional to that of the charging and discharging current. And as the charging and discharging current is much higher for this BiCMOS, so the slope will also be lower in case of BiCMOS. And you can also notice from this plot that for small load capacitance region, that is for particularly this region, the performance of CMOS is better than that of BiCMOS, which is also mentioned here. The main reason is that for lower load capacitance, the parasitic capacitances associated with the bipolar transistor in case of BiCMOS logic family will be the dominating capacitances, and the advantages given by this high driving capability in case of CMOS is just cancel out due to those parasitic capacitances. However, for higher load capacitance, the total capacitance will be dominated by the output capacitance, and there the BiCMOS logic will show the superior performance. So please remember that for lower load capacitance, the CMOS performance will be better, and for moderate to high load capacitance, the performance of BiCMOS would be better. But from the application point of view, the use of this BiCMOS is only intended when we need to drive one large load capacitance. So from that point of view, we can again say the performance of this BiCMOS logic family is far superior than that of its CMOS counterpart. If we try to position the CMOS and BiCMOS in terms of their delay and power dissipation in a same plot, then probably we have to put their positions as shown in this figure. For BiCMOS, the delay is lower than that of this CMOS. So you can see from this figure, for BiCMOS, delay is lower than that of CMOS, but in terms of power dissipation, BiCMOS power dissipation is slightly higher than that of this CMOS, which is due to the incorporation of bipolar technology in this BiCMOS logic family. So this gives a brief comparison between CMOS and BiCMOS logic family in terms of their delay and power dissipation. In spite of all these advantages, BiCMOS logic family has also some disadvantages or issues. And to discuss the issues related with this BiCMOS logic family, let us consider the inverter circuit. So this figure shows the circuit diagram of BiCMOS inverter, where if this input is equal to 0 or the input is low, can you comment on the magnitude of V out? It is expected that when this input is low, output is high. That is fine. But what should be the magnitude of that high voltage? Can this V out reach really to equal to VDD? The answer is no. V out cannot reach till VDD. The maximum voltage of V out can only be equal to VDD minus V of BE, Why? Because this V of BE, or the base to emitter voltage, whose value for silicon MOSFET, as you know, is around 0.6 to 0.7 volt, this has to be applied across the base to emitter terminal to keep this NPN BJT on, right? Because you can think even in this way, when you apply this V in equal to 0, then this is on, this is on, so there is a direct path, and this current will start to charge this capacitor, and the V out will start increasing, right? Now when this V out will reach equal to VDD minus V of VE, okay, then the current flowing through this will be off, because then at that point this transistor, this NPN transistor will turn off, right? So the maximum voltage that this V out can reach is VDD minus V of BE. Using the same token, we can also say, like, when this V input is equal to VDD or high, the minimum voltage of this V out can only reach till V of BE, because here also you can think in this way, when this is VDD, this block is off, this block is on, so this, which is this capacitor which is initially charged, now start discharging through this MOS as well as this BJT, right? Now again, to switch on this BJT, the minimum voltage V of BE has to be applied across here. Now once this V out during discharging become equal to V of BE, this transistor becomes off, so it cannot discharge any further. So the minimum output voltage which is possible for this circuit is equal to 0.7 volt. So as you can see here, then the output voltage swing is not from 0 to VDD, but instead it is from V of BE to VDD minus V of BE. So which can also be reflected if you plot the voltage transfer characteristics of BiCMOS inverter. For example, if this VDD is equal to 5 volt, then the VTC will look something like this. So this is 0 to 5, this is V out, 0 to 5, this is V in, so VTC is this. So you can notice here, the maximum voltage, output voltage of this V out can reach is around 4.3 volt, and the minimum output voltage this V out will be around 0.7 volt. So we will not get the full swing as we used to get in case of CMOS logic circuit, right? I think you have noticed that, right? Another disadvantage or issue of this BiCMOS logic circuit in its current form is that there is no path for the reverse base current. That means the base charge which is stored in the base terminal or in the base of this BJTs, this cannot be drawn out. Okay, let us explain it in bit more detail. Please try to recall the operation of bipolar junction transistor. You already know that in order to switch off the bipolar junction transistor quickly, one need to take out the stored charge in its base. The stored charge in the stored charge in the base of a bipolar junction transistor can be taken out in form of its reverse base current. So for high speed devices, we should have a path for that reverse base current to come out. Let's check whether that path exists for this BiCMOS inverter circuit or not. Suppose this V in was initially 0. So when V in is initially 0, this block was on, this block was off. So this bipolar junction transistor was on, and this capacitor has charged till VDD minus V of B. Now when this V in is switched from 0 to VDD, we expect that this block should turn on immediately and this block should turn off immediately. So that will happen for this block. When this V in switches from 0 to VDD, this bipolar junction transistor turns on immediately and starts discharging this capacitor. But what about this bipolar junction transistor? Because when V input is VDD, this MOSFET is off. So the stored charge in this base has no path to come out, because this, you can see, this is type of floating, because this is now off. So it will take some time for this bipolar junction transistor to change its state. Again, you remember, there will be one path which is trying to discharge like that, and there will be one path which is now charging like this. So which will hamper the overall switching speed of this total circuit. So it is very important that one should provide the a path for the reverse base current, which does not exist for this BiCMOS inverter circuit in its present form. The same situation can also arise for this circuit when V in is switched from VDD to 0, but in that case the problem will come due to this bipolar junction transistor. Please think about it. So this no path for this reverse base current of this bipolar junction transistor, okay, will significantly impact the switching speed of this BiCMOS logic circuits, right? And this is one of the major concern, right, for this type of circuit. So what can be done to solve this? The solution is quite easy only. So this was the circuit that BiCMOS inverter circuit that we have discussed so far. But just in that circuit, what we have done, we have added two NMOS transistors. You can see one transistor here, another transistor here, in this fashion. Okay, just to addition of these two transistors will solve that problem. Let's see how. Before going to see how, let's see the connection of this. So this V in was initially connected with only with this PMOS. Now this V in is also connected with this PMOS as well as the additional NMOS that we have now connected, and the other NMOS which is now connected here, that gate is now connected with the base of this BJT. Okay. Now see its operation. When this V input is equal to 0. So when V input is equal to 0 for this circuit, then let's see what is happening. When V input is equal to 0, this PMOS is on. As this PMOS is on, so there is an ID current will flow, that will also switch on this bipolar junction transistor. What about this NMOS? This NMOS will be off, this NMOS will be off, and as this is the high voltage here, so this will also turn on this NMOS, right? Okay. What about this bipolar junction transistor? This will be off because this transistor is off, so no base current here, right? It is now actually grounded. So this is off. So you can see there exists a path, though the current will flow through this bipolar junction transistor as well as through this NMOS and charge this output capacitor. Okay. Now, what is the function of this transistor, this additional transistor that we have added? So for this particular transistor, it is off now, so it is not performing any action now. But this particular transistor, see, this is now on because it is now connected with here, and as this is on and this is connected, and this for this transistor, the drain terminal is connected with the base of this bipolar junction transistor. So as this is on, so this bipolar junction transistor will find a path to discharge the stored charge in its base through this NMOS. So you can see we have indicated here that this is a base charge removal. This is the path for the base charge removal. Okay, so these two NMOS are this has been used to remove the charge from this base. Okay, this is now working for V input when the V input is equal to 0. Okay, so let us also check when V input is equal to 1 in the next slide. But before going to that, just want to mention one point here. So, as what is the primary function of this NMOS? The primary function of this NMOS is just to remove the stored base charge from this BJTs, right? So, as the function is only to remove the stored base charge, so it is not important to use to make this transistor very large. So, we can use a very small dimension transistor as well, these two transistors, right, that has been mentioned here. Okay, and now let us check what will happen in case of when V in is equal to 1 volt, when V in is equal to 1 or V in is high. So, when this V in is high, so now this PMOS is off, this NMOS is on, this NMOS is on. As this is off, this is also off. As this is off, so this NMOS is also off, this is on, this BJT is also on, right. So, you see that now the capacitor will discharge through this MOS as well as this through BJT, and now this NMOS is off, right. So, you can see it is similar to that of previous circuit, but for this one, for this part, you see these two are off, but this NMOS is on. As this NMOS is on, now this can remove the stored charge in this base for this bipolar junction transistor. Till now, we have primarily focused on the BiCMOS inverter circuit, right? But what about the other logic gates in BiCMOS family? For example, 2-input NAND gate. How that will look like? Let us see it here. So, 2-input NAND gate or NAND 2 gate in CMOS, it will look like something like this. What about is BiCMOS implementation? In BiCMOS, 2-input NAND gate will look like as shown here. Let us first try to find the similarity between this CMOS NAND 2 and BiCMOS NAND 2. See, these two PMOS which are connected with input A and B, they are in parallel. See here, that is also the same. These two PMOS which are connected with A and connected with B, now they are in parallel here, right? Okay. These two NMOS which are also connected with the two inputs, they are in series. These two NMOS which are also connected with input A and with B, they are also in series. So, that part is similar, right? Okay. Now, in BiCMOS, you know, two bipolar transistor has to be there. So, this is one bipolar transistor, that is, this is another bipolar transistor. Okay. You know, in the last slide only we have discussed, there should be also the path for base charge removal or base charge reverse base current path. Okay. So, we have to provide that. So, one NMOS transistor has been used here, okay, which can remove the charge of this bipolar junction transistor is shown here. Whereas, for this case we need two NMOS transistor, okay, as shown here. Okay. With one of the NMOS we have to connect with A, and the other NMOS we have to connect it with B. So, that is the new thing here, right. Now, this base has to be connected with the gate of this NMOS. That is similar to that what we have done in last slide. Okay. Now, let us see its operation. Okay. So, for operation, let us consider first first case when A equal to 0 and B equal to 0. So, all in red. So, please check the color here. So, when A equal to 0 pointed in red, B equal to 0 also pointed in red. So, what is happening? When A 0, B 0, this PMOS is on, this PMOS is also on, these two NMOS are off, these two NMOS are off, okay, what about this NMOS? Now when these two are on, this is a high voltage, so this will be on. So remember that this will be on. So as these two NMOS are off, what about this BJT? This BJT will be off. What about this BJT? As these two transistors are on, high current is flowing through here, so this will BJT is on. So this BJT is on, this BJT is off as indicated in red. Please follow the same color. Okay, so this is on, this is off, so their current can flow like this and it can charge the output load capacitor CL. Okay, so what will be the output here? The output will be high because the capacitor is now charged. So you can see here, when we give input A, input B, output is high. So in terms of truth table, if you write, when for 0 0, output is 1. Right, now here you see these two transistors are off. Okay, so as these two transistors are off, so you can see this this is now open circuit. Okay, but what about this transistor? This NMOS is now on. See the red mark? As these are on and this BJT is off, so the stored base charge in this BJT now can be removed by this NMOS. Right? Can you follow it? Yes. Now let us consider the second case when input A is equal to 0 and B is equal to 1. So pointed in green color. So A equal to 0 and B equal to 1. So for this case, this PMOS will be on, but this is off. Similarly, this NMOS is off, but this is on. This is off, this is on, but as only one of them is on, so still there will be a high drain current which is flowing through here, which is acts as a base current. So this BJT is also on. Okay, but you see here, this here one of them is on, but as they are in series, so finally no current can flow through this base. So this transistor or this BJT will be off. Okay, so there exists only one path for the current to flow from this BJT to the CL and charge it. Okay, so the what will be the output for this case? Output will be equal to 1 for this case. Okay, now in this case also this transistor is on. As this transistor is on, okay, it will try to remove the stored charge at its base at the base terminal of this bipolar junction transistor, right? Okay. The other case where A equal to 1 and B equal to 0, that will be similar to this case too, as pointed out here. You can try it yourself, and here the output will be still be equal to 1. So for 1 0 combination also, output will be equal to 1. What about the case for when A equal to 1 and B equal to 1? So when A equal to 1 and B equal to 1, pointed in brown color, so these two PMOS are off. As these two PMOS are off, no current here, so this transistor is off. That is the first case. These two transistors are off. But see here, these two NMOS are on. As these two NMOS are on and they are in series, so and this is off, right? This BJT is off. So now the stored charge at its base now will be discharged, okay, through these two NMOS. Right? It has been pointed here, like base charge removal from here. Fine. Okay. Now let's see what about here. Now for this case, this NMOS is on, this NMOS is on. Okay. What if these two NMOS are on? So high current flowing through here, which will make this transistor also on. Okay. So that means if the capacitor is now previously charged, that will now be discharged through this bipolar junction transistor as well as through these two NMOS. Okay. What about this NMOS here? Now as these two are off, so this is a low voltage, so this will not able to turn it on, so this will be off. Okay, so this is now an open circuit. Okay, so as this is now discharging, So what will be the output voltage? Output voltage will be equal to 0. So you can see here for 1-1 combination the output voltage is equal to 0. So you see this truth table, which is really the truth table of 2 input NAND gate. Okay, this justifies the operation of BiCMOS NAND 2 gate. I request you to notice here one more thing, that is this part, right, is exactly same as that of this CMOS NAND 2 part, right? And what about this part? This part is same as that of this part, or the pull down part of this CMOS logic, right? Just notice it, we will use it after 1 or 2 slides, this one. So probably now you can also think of implementing this NOR 2 gate, okay, whose CMOS representation is shown here. So can you think of how its BiCMOS equivalent will look like? Yes, you are right. It will look like this. So see here again, try to compare this CMOS and its BiCMOS counterpart. So for this 2 PMOS where 2 inputs are connected, they are in series. 2 PMOS where the inputs are connected, they are in series. 2 NMOS where the inputs are connected, they are in parallel. 2 NMOS, okay, where the inputs are connected, they are in parallel, right? Now these are the 2 bipolar junction transistor. This is the NMOS transistor to remove the base charge out of from this bipolar junction transistor, and this is the combination of NMOS to remove the charge from the base of this bipolar junction transistor, right? Operation wise, I think you can try to you can do the same analysis as we have done in the last slide, and you try to check it out that this V out is actually represents the output of an 2 input NOR gate. Okay, here also if you check one more thing, that this part is same as this CMOS NOR 2 part, right? And this part is same as the pull down network part of this CMOS NOR 2 gate, right? Now in the last slide also we have seen the similar thing, right? So suppose if you have asked to draw the BiCMOS implementation of any other logic gate, can you do that? Probably the next slide will help you in that. So first you have to draw the CMOS implementation of the particular gate, then use the same implementation here, and its pull down network or the NMOS part you have to put it here and make the circuit like this. So this is a general rule, so you can follow this rule and make implement any other logic gate in BiCMOS logic family. Remember the issue of VB voltage drop in case of BiCMOS logic circuits? Yes, right? Okay, let us see how does it impact. So let's consider a case where one inverter is driving another inverter. Okay, this is the CMOS implementation of one inverter followed by another inverter, and the final one is driving another the load capacitor CL, and this one is the representation while we use the BiCMOS logic family. So this is the BiCMOS inverter, this is the BiCMOS, another BiCMOS inverter. Let us consider the input here is low, 0. So the input here is 0. So what will be the output? Output will be high, but we know that it cannot reach to completely to VDD. So the output that we will get here, that is VDD minus V of B. So if this is the output, that will be the input for the next inverter. So if this is the input for the next inverter, okay, among which you remember that V of B, the voltage has to be dropped across this BJT to turn it on, right? So what is the actually voltage dropping across this NMOS? That is nothing but VDD minus 2 of VB, right? So if this is the gate to source voltage for this NMOS, so what is the current ID through this NMOS? That will be proportional to VDD minus 2VBE minus VTH square, proportional to, right? So that is the current flowing through this, right? You remember that we have discussed. Then what is the total discharging current? The total discharging current will be 1 plus beta into that ID. So it is 1 plus beta into VDD minus 2VB minus VTH square, right? Now let us consider for this case. Okay, if here also the first inverter input is 0, but then the output will be here VDD. So this VDD output will be driving the next inverter. So what will be the discharging current for this CMOS? You know, for this CMOS, the discharging current will be proportional to this VDD minus VTH, that square only, right? So if we now take a comparison, take a ratio of this discharging current due to this BiCMOS technology and then this CMOS technology, so this will be given by this, right? Now what is this V of B? V of B is the built-in potential in PN junction. So that is not going to scale down, that is more or less constant, around 0.6 to 0.7 volt, right? And here you can see it is 2 times of 0.6 or 0.7, which is around 1.2 to 1.4 volt. So now the issue of scaling down of this VDD, you know that, right? As you scale down the device size, the VDD will also scale down. So as we are scaling down this VDD, then see this term, this VDD minus 2VE minus VTH, this term will now reduce significantly because of the presence of this 2VE term. So basically the ratio of ID BiCMOS by ID CMOS, this decreases as we scale down this VDD. So the advantages of this high drive current in case of BiCMOS circuit will not be that significant for scale devices where VDD is quite low. Finally, I would like to thank you for your time.